Welcome all. We're just going to give people a moment or two to join, and we will start shortly. Welcome all. We'll start shortly. Well, may I welcome you all to this first webinar hosted by the Institute of Physics and Engineering in Medicine on developments in photoplethysmography. We're very glad that both you attendees are able to join us, and also that our three speakers here today have offered to give us talks on the topic of simulating photoplethysmography signals. This webinar is being recorded and it will be made available on the IPEM website. A link will be sent to all registered delegates as soon as it's available to view. During the event, we'd encourage you to ask questions, and please do so by typing them in the Q&A box at the bottom of the screen. We'll save questions for the end of the webinar when we'll have a panel discussion, so we'll address all the questions together. So today, we have 3 talks on simulating photoplethysmography signals, which will encompass both the engineering techniques used to simulate the signals and applications of simulated signals in research studies. Dr. James May sends his apologies. He is unable to attend due to unforeseen circumstances. So I'd like to introduce our first speaker, Dr. Andrius Solosenko. He is a researcher at the Biomedical Engineering Institute at Kaunas University of Technology in Lithuania. Andrius and his colleagues have done fantastic work on simulating photoplethysmography signals during arrhythmias, and they've recently made their work available on PhysioNet. Andrius, thank you for speaking to us today. We're very much looking forward to your talk.
Greetings, and thank you for inviting. Right, I'll share my. Right, I'm going to introduce our model for simulating photoplethysmography signals, which was intended for assessment of atrial fibrillation detection algorithms. Right, since I'm the first speaker, I'll briefly introduce the process of PPG acquisition. So basically, it is the difference of light absorption in oxygenated and deoxygenated blood, which results in these typical pulsations. So what was the reason to simulate PPGs in our case? The main need for that was that we needed something to assess our PPG-based arrhythmia detectors. It was the main reason for development of that simulator. And there was a lack of annotated PPG signal databases. But since we had other databases which included ECG signals, such as in those available in PhysioNet, like atrial fibrillation database, we thought that maybe we could use these databases to generate the PPG. So we'd need to acquire our own database and then make manual annotations. We could just take that database and we could have annotated PPGs. provided that series are annotated. And with simulated PPGs, we have an ability to control signal-to-noise ratio, which is important for the assessment. Right, so the process of development was rather quick, I would say. So the original intent was to develop that, as I said, for atrial fibrillation detection algorithms. And at first, I had very little expectations about that kind of algorithm. So after initial results, I thought that they are quite promising, and they came up rather quickly. So after some more work, I noticed that the simulated PPGs are way too similar to the real ones. So we proceeded with that kind of work. And the principle of simulating PPGs is that we have R series as an input to that model. The R series could be either acquired from the ECG signal or by using synthetic generators. Next, we have the sequence generator, which generates separate pulses. I used many pulses from various databases, but since there are way too many pulses, we just left 5 pulses which were described in literature by Dober. So these are the main pulses we're using currently in our model. And next, these separate pulses are then connected into the sequence to generate the PPG signal. And to back my claims that they are quite similar to the real PPGs, here you can see short signals of atrial fibrillation and the resulting simulated PPG signal, which is on top of the real one. And as you can see, the difference is quite minimal compared to the real one. The same goes with the atrial premature beats and ventricular bigeminy. Although the RR intervals in the bottom are correlated with DCGs, but there are some cases like in ventricular bigeminy where intervals extracted from the PPG signals is way different than those in ECG. It's due to the pulses being merged together. And our recent work was about the detection of tachycardia and bradycardia, and my colleague fine-tuned that simulator to better represent the differences in amplitude in those cases. So you can see an example of bradycardia and tachycardia, both the real ones and simulated signals. And I'll talk a bit about the practical application of that simulator. So the first, of course, was the testing of the PPG-based atrial fibrillation detection algorithm. Then it was used in modeling of artifacts in PPG signal. The more recent study was to use that model to train the convolutional neural networks for the detection of tachycardia and bradycardia. And we're also using that model in a hardware PPG simulator as well. So in the application where we used it for the atrial fibrillation detection, it was used for the setting of some of the parameters. For example, the threshold for signal quality assessment. And we use signals from long-term atrial fibrillation database from PhysiNet to generate the PPG signals. And these PPG signals with different pulse types were used to set the SQI threshold. And another known database, the popular one, which is FDB, was used to assess the developed algorithm by changing the SNR. So yeah, we were able to to see how our model or how our algorithm performs during various types of noises. I'll note that the noise here was also synthetic, but it was acquired by using that same model, and then we used adaptive filters to extract the artifact from the real PPGs and use system identification to then use that kind of noise and add it in PPGs. So it's quite realistic, but still it was stationary. The next application was to model PPG artifacts. My colleague did that. She used the same principle to generate the PPG, the model one, and subtract it from the real PPG to obtain the artifact, which then was used to model various types of artifacts, which was classified in different cases. Well, when we were moving hands, when we are walking, so she classified different types of artifacts, and we extended this simulator by adding that kind of noise to our model. Right, the more recent application was to use that kind of model in tachycardia and bradycardia detection. So here you can see real PPG segments with corresponding scalograms, which were used as an input to the convolutional neural network. And here are the simulated signals, which were acquired by using also Physinet databases, which contained ECGs with bradycardia and tachycardia. So as you can see, they are very similar to those which are real. So these signals were used for training the neural network. And when we tested on that real database, which was quite small, so we couldn't use that database to train. We didn't want to use cross validation, so we use simulated signals instead. And finally, our intent was to use that model in our hardware simulator, also for testing the atrial fibrillation detector in our wrist-worn device. Here you can see the prototype of our wrist-worn device and our simulator. So it runs, that simulator runs inside and generates signals which are recorded by the wrist-worn device, and it starts vibrating when it detects the arrhythmia. Right, as Peter mentioned, we recently published our simulator in the Physinet database. It is in both as a GUI, and we have source files also attached to that database. The GUI was created for maybe an easier use of that simulator. You have many options. Still, we hadn't get any feedback yet, so if somebody tries using that, it would be nice to hear any feedback. Maybe we'll get some bugs or something, right? So, and there are possible few further extensions and improvements for our model. We think that maybe we could add respiration into account. Of course, since we're using PCGs, real ECGs, due to respiration, we have a difference in our intervals, that is in the heart rate. So to some extent, we are able to take that into account, but not fully. And we would want to add realistic baseline wandering. Since it was out of scope for the primary application, we didn't do that yet. And application would be to assess the pulse arrival time with that kind of simulator, as well as oxygen saturation. There are that kind of simulators available already, of course, but want to extend our own a simulator with that kind of functionality. Right, so and that is all for now, and thank you. Maybe you have any questions?
Thank you, Andreas. That's a fascinating talk and a fantastic body of work. Congratulations to you and your colleagues.
Thank you.
We will hold questions for the panel discussion at the end. So thank you
Right.
for the questions submitted so far. And I'll introduce our second speaker, who is Cheng Ding. Cheng is a researcher at Emory University in the USA, and he and his colleagues are pioneering the use of generative adversarial networks for simulating PPG signals. And it's a fascinating approach. And Cheng, we're very much looking forward to hearing your talk today. Thank you.
Thank you, Peter. Let me share my screen. Okay, is everyone okay to see?
That looks good. Yeah.
Okay, so yeah, thanks, Peter, again. So good afternoon, everyone. I'm Chen Ding, PhD student in BME from Emory University and Georgia Tech Joint Program. So today I have a quick introduction to the generative adversarial network, GAN for short, and how we use the GAN to generate a synthetic PPG signal. So first, why can be named? So the ultimate goal is we want to learn a generative model. To achieve that, we choose to use deep neural nets and train the neural nets in an adversarial way. So here's a high-level example of the GAN. Normally, GAN has two components, generator and discriminator. The goal of generator is to generate the fake images, and the discriminator is to distinguish a given image is fake or real. So the whole process is like, as shown in the right side, is like one criminal group is making fake currency, and the police group is trying to tell if the money is real or not. So at first, the criminal group knows very little about what the real money is, but after several iterations, they will learn gradually until the police group cannot tell the difference anymore. So this is a more detailed example of GAN architecture. So we have a generator which takes the random noise as input and generate a fake image, and the discriminator will take the both image from fake and real and tell if it's real or fake. So our goal is to fold the discriminator. And below is the cost function or loss function of the GAN. Basically, we want to maximize the discriminator's error, which means it can be folded. And also we want to maximize the discriminator error on the generated data. This is a basic idea of GAN. Also, training GAN is also very important. Here's a simple introduction how the train is done. So in the figure, black dots means the real world data, and the green line is the distribution of the generated data. And the blue dash line is the discriminator. So at step A, everything just initiated. The blue line is just random guess, and the generated data is from a simple distribution Z. So at step B, the discriminator got trained, and it will find the best boundary to separate the real and the fake. And then step C, based on the results from the discriminator from step B, the generator will be trained towards the real data. So after many iterations, ideally, the generator is getting perfect match with the real data, and the output of discriminator is fold, and the output of discriminator is 0.5 everywhere. Here's some examples from the original paper. As we can see, we can tell that the GAN is able to generate some realistic image, but the quality is still not good. And one important and popular new design of GAN is introducing the convolution architectures. So compared to the traditional GAN, convolutional layer is better at extracting significant features. And from the results, we can see that the generated images are with better quality. So in our group, we are submitting one paper about using GAN on the PPG data for atrial fibrillation detection. And so we are naming it as log spectrum matching because we are introducing the spectral loss into the loss function. So our PPG data were collected from patients from UCLA and UCSF in America. And you can observe that after the processing, there's a class imbalance issue in our training data. So we're thinking maybe we can use GAN as a data augmentation method to generate more synthetic PPG to enrich the training data and make it balance between two classes. So on the left side is the overall workflow of our GAN. So we have two innovations. The first is we introduce the frequency domain information into the loss function. We call it LSM loss, which we'll introduce later. And also, second innovation is we design a new generator, which will generate the same length of the PPG signal with the same length of PPG signal with the same length of input noise. So in the conventional design, the length of the random noise is just 100. Is an arbitrary number. But in our case, we design an architecture which can take different lengths of noise and generate the same length of PPG signal. Okay, here is our main innovation. We call it LSM loss. So for the generated signal, we will generate two losses. As you can see in the left figure, we first cut off each PPG signal into several equal length blocks. And for the blocks with the same index in real PPG and the synthetic PPG, we will calculate the distance between the matched blocks in a frequency domain. Also, we will also calculate the difference between blocks within one generated PPG, and we call it self-consistency. So the final loss is as you can see in the bottom right, the final loss as LSM loss is defined as the linear combination of three losses. The first one is the cross entropy, which is traditional conventional loss, and with our two losses. Also, for each block, we have two options to aggregate blocks into one single value. So we choose either max, taking the max value, or taking the mean value of all the blocks within one single PPG signal. So F is like two choices. And then we use the synthetic signal generated from our GAN to make the training set balance, and use the resonate, which is a very popular deep network, train on this new and balanced training set. And table 1 shows the performance of different data mutation methods. We can see using data from our GAN to train the classifier can improve 14% of accuracy compared to training on the original unbalanced data, and 3% more compared to other baseline methods. And table 2 shows the hyperparameter we select for the two losses. And table 3 actually investigates the, I missed one part, is for the non-AF, and most of the time is normal size rhythm. And the lambda 2 means represents the weight for self-consistency. And 3.0 means it pay much more attention on the self-consistency for the non-AF signals, which is expected because for the NSR, the periodic is most important, regularity. And table 3 investigate the importance of hyperparameter. So when we set all the lambda as 1, which means there's no weighting mechanism. And second line is choosing the largest MMD distance instead of the least MMD distance. And from the result, we can tell that selecting the best hyperparameter can really improve the AF detection accuracy. And we also consider the signal quality. So in order to do that, we annotate the regions of artifacts in the test set. And according to this, we divided the test set into 4 groups, depend on the percentage of artifacts. So we have 4 groups, you can see from this figure. We have 0%, 0 to 20%, 20 to 60%, and 60 to 100% of artifacts within PPG signals. Here is the same model from the previous experiment, test on each signal quality group, and compared to the baseline, our GAN has the best performance, except for the last group, when the signal quality is really bad. And lastly, we use PacMap. It's a dimension reduction techniques, which can also keep the same distribution when reduce the dimension. So we use the PacMap to reduce the signal dimension to 2, so we can plot the signal in a 2D plane. And all the 4 subplots here are the same, but we just highlight the related category in each small subplots. So we can see that from a traditional GAN of conventional GAN baselines, the signal generated from those only capture parts of the distribution of the real AF, but the signal from our GAN is more diverse and has similar distribution to the real signal in the AF cases. And for the non-AF case, similar phenomena happens. You can see that for the baseline GANs only capture parts, but our GAN has like a near distribution, closer distribution to the real signals. This is some reference list, and that's all. Thank you.
Thank you very much, Cheng. Great to see how comprehensive your approach is, particularly in that last visualization picture, and fascinating to hear about the choices you made in designing the approach. Thank you. We will take questions after our final speaker, who is Dr. Jordi Alastrui-Arimon. Jordi is a researcher at King's College London in the UK, and he has developed approaches for simulating pulse wave signals throughout the body based on physical principles of blood flow. And he's used this approach to gain insights into both physiology and clinical applications. Jordi, thank you very much for speaking to us today. We're looking forward to your talk.
Thank you, Pete, for the introduction and invitation. Hi, everyone. I'm delighted to talk today about how we can conduct research with simulated PPG signals for hemodynamic studies. Using pulse wave computational blood flow modeling, we can simulate the PPG together with other cardiovascular signals, such as blood pressure, blood flow velocity, luminal areas, and we can do that at common measurement sites in the body. And these signals are all produced by the propagation of the pulse wave, which is the result of the beating heart interacting with flexible arteries. And that's why these signals are often called pulse wave signals. These signals can be measured in vivo using a variety of devices, including wearables, and are influenced by the heart, the vasculature, and also the respiratory and autonomic nervous systems. So that makes these pulse wave signals a rich source of information to assess human health, including cardiovascular health. Developing and testing algorithms and indices to assess pulse wave signals requires comprehensive data sets measuring large clinical cohorts. And unfortunately, acquiring these data sets is usually a complex task. And on the left, you can see some of the issues that we may encounter. And to facilitate this process, we have created data sets of simulated pulse wave representative of samples of real subjects using computational blood flow modeling. So we have developed a methodology to create in silico pulse wave data sets, which consists of the 5 main steps listed here. And Peter has actually been key in designing and implementing this methodology. So once the database is created, we need to verify that the simulated pulse wave signals are representative of samples of real subjects. And we can do that by comparing simulated pulse wave with in vivo data from healthy subjects from the clinical literature. So here you can see comparisons in a few arterial locations showing similar changes in pulse wave morphology with age to those measured in vivo. And that also goes for the PPG signal that you can simulate at the finger here at the bottom of the image. And we have, and we can also compare pulse wave indices between the simulated and in vivo pulse wave. And quite remarkably, we found that simulated pulse wave indices and shapes, also the shape of the morphology from aortic root to digital artery, compare very well with in vivo data across different age groups. So for the remaining of my talk, I would like to show some clinically relevant studies on how in silico pulse wave datasets can help us design and test algorithms and indices of pulse wave analysis, including machine learning models, understand the potential shortcomings of existing technologies, and also understand the mechanisms underlying hemodynamic observations. And the first study is the detection of abdominal aortic aneurysms, or AAAs, from pulse wave analysis. And these aneurysms are usually asymptomatic until rupture, which is unfortunately associated with very high mortality. And therefore, early detection of AAAs is really of paramount importance in reducing mortality. But the problem here is that most AAAs are detected by medical imaging accidentally. So incidentally, sorry. And we are investigating pulse wave analysis methods based on machine learning that are more convenient and also less expensive for large scale screening than medical imaging exams. So we have created a machine learning architecture based on the recurrent neural network to detect AAAs from the PPG pulse wave. And our method was trained and tested using the PPG signal measured at the finger from a data set of over 10,000 virtual subjects with and without aneurysms, AAAs. And the model had a very high sensitivity and specificity in early detection of AAAs, as the confusion matrix and receiver operator characteristic curve show at the top. We then simulated a more realistic scenario during testing by adding random noise to the PPG pulse wave. And that reduced the sensitivity and specificity to above 86%, as you can see at the bottom of the image, which still suggests that the trained machine learning model was competent in classifying normal and aneurysm conditions using a digital PPG pulse wave that had less resemblance to the pulse wave of the training set. So the in silico data set seems to be useful when it comes to the design and testing of machine learning models. The other clinically relevant study that I would like to show you is the estimation of the stiffness of the aorta, which is an important marker of vascular health. And indeed, increased arterial stiffness has been shown to be an independent predictor of morbidity and mortality from cardiovascular disease. Aortic stiffness cannot be directly measured in vivo, but we can use the velocity at which the pulse wave is traveling to as a surrogate for aortic stiffness. As an example, the plots show that the probability of overall survival on the left and probability of event-free survival on the right increases considerably with the increasing pulse wave velocity in a cohort of end-stage renal disease. So several clinical methods have been proposed to measure pulse wave velocity from pressure or flow waveforms measured at two arterial sites. So for example, those shown on the sketch on the left, and then typical combinations of waveforms are shown in the center. And the sketch on the right illustrates the foot-to-foot method for estimating aortic pulse wave velocity using two pulse waveforms. So the method calculates pulse wave velocity as the ratio of the distance between the two measurement sites to the time delay for the foot of the pulse wave to travel from one measurement site to the other. And distances are typically measured from surface markings, and the time delays by identifying the feet of the two waves using pulse wave analysis. So using a database of over 3,000 virtual subjects, we could test existing foot-to-foot methods and show that actually only the carotid femoral pulse wave velocity is a good indicator of aortic stiffness, which is in agreement with clinical studies. So we could, but with the in silico data, we could also provide a mechanistic explanation of why this is the case. So results on the left show that the carotid femoral pulse wave velocity correlates well with aortic pulse wave velocity across a wide range of values of true aortic stiffness. However, on the right, we can see that brachial ankle pulse wave velocity overestimates pulse wave velocity, the aortic pulse wave velocity, since it is related to the stiffness and also to some extent the geometry of more peripheral muscular arteries than the aorta. And also we found that carotid radial and also femoral ankle pulse wave velocity do not capture really aortic stiffening. They are therefore not so good surrogates, right, for aortic stiffness, which is also in agreement with some in vivo studies. So the carotid femoral method is an accurate method that is widely used in clinical research. However, it requires skill operators to acquire the data, and its applicability is limited to the clinic only. So using in silico data, we are investigating methods to estimate pulse wave velocity from the PPG waveform. And the idea here is that is to use pulse wave analysis to identify fiducial points on the waveform by calculating first, second, and even higher order derivative of the pulse wave signal. And then indices can be calculated from these points. And actually, Peter is leading this research. And here we have some results. So we have shown strong correlations with aortic pulse wave velocity of indexes calculated from pulse wave morphology. However, these indices are influenced by other cardiovascular properties, such as heart rate, stroke volume, and also the diameter of large arteries, which may affect their ability to stratify patients. And using in silico testing, we could actually study the physiological determinants of each index and provide a mechanistic explanation of why, for example, the third index is performing better than the other two. So to conclude, we have seen that pulse wave signals, including the PPG signal, can be modeled accurately and efficiently using computational blood flow modeling. In silico databases provide a quick and inexpensive route to initial development and assessment of pulse wave algorithms and also indices. And we can do that across a wide range of cardiovascular conditions, and also in a relatively quick and inexpensive fashion. And lastly, in silico testing enables us to understand physical mechanisms underlying the correlations observed from populations of real subjects, and also train machine learning models across a wide range of physiological conditions. And they may also be useful for interpretability of neural network models. So moving forward in silico testing combined with machine learning and also the proliferation of wearable sensors really provides new opportunities for assessing cardiovascular function within the wider population using pulse wave analysis. So I would like to thank my group and funding bodies which have contributed to this research and to some extent, and thank you for your attention.
Thank you, Geordie, for that very clear presentation. And I particularly appreciate the novel applications, such as identifying abdominal aortic aneurysms. Great to see where the field might be going in the future. Thank you. So we'll now move on to a panel discussion. And during this time, please do type any questions you might have in the Q&A at the bottom of your screen, and we will answer them in turn. Firstly, I'd like to start with a question from Professor Panikos Kyriakou, who asks, in the opinion of the panel, what are the current bottlenecks that prevent the high volume of PPG research from translating into devices which are approved by regulators and used in the clinical setting?
Perhaps I can start, just give my opinion coming from blood flow modeling, which I wouldn't consider myself as an expert, right, on PPG, but according to my experience, what I realized is that those signals that we can measure in reality, they contain lots of artifacts, right, and it's really difficult to get rid sometimes of those artifacts, the noise associated to those artifacts. I'm not sure what's the best way to move forward, but I've seen that there are techniques to remove noise, right, so using machine learning to reduce noise. And actually, from my angle, from my approach, what we can do is we can simulate using physical principles. We can simulate those signals, and then we can add noise and sort of in a controlled way, and that might be able to help going in the direction then of finding ways of removing the noise. That's what, according to my experience, what I can say.
Thank you. Yeah, so tackling the problem of noise and using these approaches to help us overcome it. Any further comments?
Yeah, and I can think about one is the variance between different patients. So even for for example, atrial fibrillation patients, different people can have different morphology on the PPG. So to do a patient-specific modeling or detection is a tough question. Problem to solve.
Yeah, I would agree with the colleagues that the main reason hindering is the artifacts. So we went the easier way, to detect the artifacts, to find the corrupted parts of the signal. And in order not to get into more details about the morphology, and we're just using peak-to-peak intervals. And that combination proved to be quite successful in detecting atrial fibrillation. Maybe not in all parts, but in most cases, I would say. So at least what we have now, so this proved to be the best solution. Of course, we want to somehow to clean those signals, but sometimes it's even impossible, because either we are not having the signal in that part of the recorded signal, or it's impossible just to recreate or to clean that part. Yeah, so that's just my comment.
Thank you all very much. And Panikos notes perhaps the lack of confidence where the PPG comes from, which we will address in our next question, and also the lack of standardization in acquiring the PPG. So let's just pick up on Panikos's comment on where the PPG comes from and move on to a question from Professor Kirk Shelley, who says, from my perspective, the complexity of simulating the PPG comes from the fact that you have two different pools of blood that are being modulated by three different physiologic systems. Specifically, local arterial and venous blood volumes are being changed by the cardiac, respiratory, and autonomic activity. I believe what makes PPG simulation a particularly hard problem is that we don't have a good understanding as to the source of the PPG signal. Given the work you've all put into simulating the PPG, have you gained any new insights into its microvascular origin?
So maybe I can explain how we have simulated the PPG signal using physics, which doesn't mean that this is really the source of the PPG signal. But basically what we are doing in those simulations, we are solving using physical principles. We are solving for blood pressure and blood flow with time. So we calculate those signals. And then we can post-process those signals to basically calculate changes in blood volume at peripheral vessels. And that's how we simulate the PPG signal. And then we compare with real PPG signals, right? And also how changes in morphology happen in simulated signals and with aging, and in real signals with aging. And those there was good agreement between the two. That doesn't mean that that's really the source. Changes in blood volume is really the source, the only source of the PPG signal, but that's what we observe from our simulations.
Thank you. Any other thoughts or comments on the origins of the PPG?
I would like to comment, of course, about the origin. In our case, when we developed our model, the main reason was, and the case was to recreate the shape. So we're calling our model the phenomenological model. So that was the main reason, just to create the shape similar to the real ones without having much knowledge into how it is created. Well, there were parts of the signal, like when you have premature beats, and the shape of the signal which results in when you have premature beats. So that was the point, to create that shape of the signal, so it represents the real ones, but without deep knowledge into how it originates, for example. Would like to know that because from comments from Jordi, I've seen difference in signals acquired from the finger and from the wrist. We want to calculate SpO2 from the wrist, and it's quite a challenge compared to the finger. For example, the signals are quite different. The baseline is quite different, and the morphology as well. So it'd be nice to have deeper knowledge into how it is acquired. Well, so maybe we could solve that problem much easier than we are doing it now. So that's.
Thanks, Andreas. Just a quick comment from me. I particularly appreciated in your presentation the distinction in, I think it was ventricular bigeminy, where you noted that the beat-to-beat intervals appeared different between the ECG and PPG. And that was one way in which the physiological origins of the PPG were kind of examined. We will pick up on your point, Andreas, on different body sites. You mentioned the finger and the wrist. Unless, Cheng, if you wanted to comment, then do go ahead.
No, I'm good. Thank you.
Great. And we'll move on to Professor Vaidotas Morozes's question, which connects with this. And specifically, he asked Jordi, is your in silico model able to simulate different morphologies of PPG? And he goes on to examine different scenarios, such as transmission or reflectance PPG, and then mentions the wrist, I guess, similar to Andreas, picking up on wrist versus finger or different sites.
Yes, thanks for the question. The answer is yes. Yeah, we can simulate using physics, so physical principles of conservation of mass, linear momentum. We can simulate those signals in a network of arteries. So we need to know input parameters on geometry, material properties of all arterial segments in the network. And then we solve partial differential equations, yeah, based on physical principles. And then that really produces changes in the morphology of the PPG signal, calculated as I explained by looking at changes in blood volume. Yes, so the answer is yes. And then, so you get those signals simulated in the model. And then because it's a model, you can do studies to understand what are the mechanisms, right, underlying those changes. So it could be, as you pointed out, reflections, transmissions, and transmitting or reflective wave. But yeah, we don't account a priori for that. So we just solve the equations, and then we can later analyze the signals if needed. Yeah.
Thank you. And finally, if anyone else has further questions, do add them to the chat, but I'll just summarize Dr. Henry Weatherburn's comments. Dr. Weatherburn mentions that there's an aortic abdominal aneurysm screening program for all over 65s in England, and asks, aren't most AAAs detected there? Also, is the data from this program readily available for validation, and in turn, perhaps applying the work proposed here?
Thank you, yeah, and for your comment. Yes, that's something, it's work in progress for us to get the funding actually first to do the study. It is true that obviously the study I show you is just an in silico proof of concept. And yeah, it requires validation in vivo. What we would like to do actually is to check actually whether by doing the training in silico, or maybe a bit of hybrid in silico and in vivo, yeah, then whether when we do the testing in vivo, whether the model, the machine learning model is still working or not. Yeah, that would be the nice test to do. Yes, it needs to be done in vivo for sure. Yes.
Thanks very much. Well, perhaps I could have the privilege of asking the last question. May I firstly thank all those who've asked questions. For me, I'd love to know what's next. What would you like to do with your models, and how would you refine your models if you could?
So perhaps I can start. So the problem with our models at the moment is that they simulate only one cardiac cycle, basically. And you know that for the PPG, variability is very important. So what we want to do is to add that into the modeling. So to simulate several cardiac cycles and accounting also for other systems in the body. So breathing, respiration is very important. So that's the direction that we would like to go towards. Yeah. And in the community of blood flow modeling, usually only one cardiac cycle is simulated, but it would be great really to extend that. Yes.
Yeah, actually, similar here. So because my main focus is on using PPG to detect arrhythmias. So I think my next step is focusing on the patient-specific detection. So when we have a large data set and train a very complex model, how do we deploy for each single new patient? This is I think is still an ongoing effort. So currently, I'm drafting actually a review paper about different techniques using PPG for patient-specific, like blood pressure estimation, heart rate estimation. Yeah, I'm drafting a review paper on this. But yeah, I got a lot of inspiration. I think that's my next step.
Thank you.
I think it's there are almost no limits to improve the model, of course. I just wouldn't want to make it more complex. We're happy that it's quite simple in implementation. And the most maybe important thing that I would want to do with it is to use that model inside the hardware simulator, which we are currently doing now. So we can test, for example, commercial devices like wrist-worn devices, how what is their performance compared to, for example, our wrist-worn device. How the heart rate is calculated in different devices. Is it similar, or there are differences, like what kind of window they are using to average the heart rate and so on. So maybe that's the modest thing that I would like to do with the model.
Thanks very much. Yeah, and that was a really promising direction coming from your presentation. That would be fantastic. Daniel Coulin, Dr. Daniel Coulin has just submitted one final question, which we will finish on, and then I will announce the next webinar. Dr. Coulin asks, what is the panelists' understanding of the second derivative of the PPG? For instance, literature talks about 5 points on the second derivative, but sometimes we see more or less. What could influence its morphology beat to beat, perhaps picking up on your discussion of wanting to model several beats as opposed to just one?
So maybe I can start again. Second derivative, well, it's my limited understanding, yeah, and again, I'm getting introduced into this topic of analyzing the PPG signal, is that it amplifies, yeah, the signal, because we are differentiating twice. And yeah, it seems actually we are at the moment, I have a PhD student working on analyzing PPG signals and trying to assess cardiovascular function, on in particular blood pressure and stiffness of the arteries. And it seems actually that the second derivative is really the key. It's the one that produces the indices, yeah, or the fiducial points, and then the indices that really could help the most if that's what we want to do in terms of assessing cardiovascular function. Obviously, another alternative route would be to use just machine learning and just fit the algorithm, the model, with the whole signal, and then the model decides whether, yeah, second derivative is the way to go or not.
Thank you, Jordi. Very helpful. Which I think leads nicely onto the next webinar in the series. So our next webinar will be on the 3rd of March, and the link for details of the webinar is in the chat. This webinar, hosted by Physiological Measurement, who are closely associated with IPEM, will focus on recent advances in photoplethysmography. And we've got a fantastic lineup of speakers looking at how to leverage the wealth of information contained in the PPG, whether it's the second derivative or whether it's other aspects. And so we'll have talks from leaders on topics ranging from cardiovascular risk assessment, cuffless blood pressure monitoring, and validating PPG technologies, building on Andreas's comment for clinical use. So I'd encourage you all, have a look at the link. Do sign up in due course. The link isn't there just yet to sign up, but it will go up in not too long. And I'd like to thank all our attendees for attending and for your very insightful questions. And finally, thank our 3 speakers. Thank you all very much. We've learned an awful lot from you today. Thank you. I'll close the webinar there.
Thank you, Peter.
Thanks, Kelly.